Okay, so if we were to imagine our sun was like a big, gigantic, round cake or an orange or something that you could cut up, you've got a picture of that just like down below here. Uh, Basically, what we can see in the center, there's a core, and that's where nuclear fusion is taking place. So that's that big plasma ball where the electrons are stripped off the protons because it's so incredibly hot and high pressure in there. So they're just pinging around, and that's where the protons are joining together, and you've got nuclear fusion producing a lot of radiation, a lot of gamma rays. So what happens to that then? Because that's obviously what, like, the energy that comes from the sun is originating there. So basically, just outside of that layer, you've got the radiative zone. So the radiative zone is basically where that the gamma rays from those reactions that are occurring inside the core are coming out, and they're just like pinging off other molecules and things that are in that area, and they're bouncing around and they're slowly making their way out of the sun. But it takes a very long time. It takes about 170,000 years to actually go from the center, like from the core where that reaction occurs. So when two protons collide, it's a bit more complicated than that, but just let's call it that. So when two protons collide in the core, it takes 170,000 years for the energy that produces to get from the core of the sun to the photosphere. And then it takes 8 minutes to get to us. So it's a really quick trip for, through space, but there's just, it's taking a very long time in the sun. So once it does eventually get through that radiative zone, you've actually got this convective zone, and that's kind of like, if you think about convection in the mantle in Earth, I guess it's a bit like that idea that, you've got hotter material rising and then cooling, and then they're going around in circles. So at this point, it's actually cool enough that the protons and the electrons have been able to join back together again, and so you've got hydrogen atoms in that section, and it's no longer plasma. And then outside of that's the photosphere, and that's where all the visible light's being emitted. And that's why we talk about, when we're looking at the sun, we're looking at the light from it, we're looking at absorption spectra, because you've got this incredibly hot, basically like this core that's acting as a black body. It's producing an entire spectrum of electromagnetic radiation, and then it's coming through the photosphere, which is actually hydrogen atoms, and that's why you're getting those hydrogen signatures in the sun's absorption spectra. So basically, if you've got all this pressure going out, why isn't the sun just exploding? And basically that's because you've actually got what we call hydrostatic equilibrium. So there's an inward pressure, and then there's an outward pressure. And down in the corner, or in the middle of the slide, you can see there's like a picture of a yellow ball, and there's some lines going out like this. So that's our fusion, the pressure from our fusion and just our thermal energy. So we've got all that heat and pressure pushing out from all of these reactions that are occurring. But there's obviously a pressure forming in, and you should be thinking now, while I'm talking about this, that can you think of a force that would be causing this pressure to be pushing something in, something that has mass? If you're thinking about gravity, you're right. So you've got gravitational weight pressure pushing in, and then you've got the fusion pressure pushing out. And in our sun, it's like a star that's in its middle age. It's kind of stable. It's very stable, actually. Don't worry about it. It's actually those pressures, like those forces, are in balance. And so we say it's in hydrostatic equilibrium, because if one of those gets unbalanced, and that can happen, and we'll talk about that later, obviously it's either going to collapse or explode.